First of all, we are actually 3 persons that will be talking today. Maybe you can stand up a little. This is Ozren from VESKI, and this is Metod from Dewesoft. And I'm also from Dewesoft, and I will start talking a little about the basics of orbit analysis in Dewesoft. So we'll start with talking about what it is used for, a little about the concepts used for the calculations, and how you set it up, the configuration with the probes, and how to mount it, and then what the results are explaining, what different results you can use to characterize different types of phenomena. So first a little introduction here. What are we talking about? What it is used for? So in principle, this is used for every time you have a shaft moving in a sleeve bearing, journal bearing, where you have not a tightened ball bearing fixed connection, but where it's lying inside an oil film, where you want it to be not touching the surface of the cage, and also you want to make sure that it is not vibrating too much. And all that is done by having this kind of setup where you have not accelerometer sensors, but distance sensors, proximity sensors, which are constantly measuring the DC offset, the static displacement of the shaft center, and also if there are any movement inside. And also depending on the thickness of the fluid and how much there is of that fluid, that can also give some phenomena you want to measure. And this is used in all industries. So you can imagine that you have these kind of bearings used for different things, and one of them is of course energy production. Hydroelectric power plants, nuclear, coal, whatever, where, for example, let's say coal or nuclear, you have a lot of steam, it will spin a turbine, and the turbine is big and it is fixtured by multiple bearings across the shaft, and all those bearings, they want to make sure that they are conditioned such that everything are run and they can do maintenance in a planned manner instead of suddenly have to shut down this critical infrastructure. And also the sizes can be from very big turbines to something a little smaller, and it's all using the same principle. One of the things we are using to do orbit analysis is tracking the rotation speed, and we do that in order to make sure that we can look at the signals and the content of the harmonics, no matter the speed variations you have. And this is the basic concept for using what we call order tracking or speed tracking analysis, where in normal analysis you're having a frequency spectra. You might have that binned in for certain speeds, but if you're having a run-up, like here, let's say it goes from 1600 to 2100 RPM, if you're averaging over that, the red curve here shows you that it will be smeared. You cannot really follow in a great manner a good signal-to-noise ratio on those components because of that. But here in the order domain, when you do order tracking, the spectrum you get out will have an axis that are independent on the speed, and therefore, no matter the speed, you will just have the vibration levels for the individual orders or harmonics, and those are directly related to rotational components of your machine. So what are we doing? We are taking a time block signal. This is a normal FFT schematics where you have a block of time and you transform it into a block of frequencies. And this block of time has a waveform, and that is shaped by multiple components of sines with different frequencies and different amplitudes. And in the frequency domain, that's pretty convenient that you can see individual sines with amplitudes. You do the same thing in the order tracking case, but before you take out this time block, you transform it into an angle block. So now you don't have samples with equidistance between the number of seconds. You can say it's not sample per second, it's sample per angle. So if you're running with a slower speed, you will have lesser samples over time, and with a higher speed, you will have a lot of samples over time because it needs to follow to have the exact same angle between each sample. When you take an FFT of an angle domain signal, it will become an auto-tracked spectrum with an order axis instead of a frequency axis. So you will have something per revolution instead of something per second. Then let's talk a little about how you connect this, because those proximity probes here, they normally need to be conditioned. They need some kind of power to it. And if you want to do that with the Dewesoft device, you can do that with, for example, the LV module, where we can excite the source with up to 24 volts, which probes like a Bentley Nevada probe or micro epsilon probe would like. Some of them don't require this, but many of them do. Some of them are supplied externally by other sources, and you only need to figure out how to get in the probe signal and not the supply. But if you also need to supply it, you will need to be able to excite it in with 24 volts excitation. So in Dewesoft, we have this application for orbit analysis where you are setting up the bearing configuration. You have the setup here. First of all, you select the reference speed source, which can be another prox probe or a magnetic sensor or an optical sensor, something that gives you a pulse that relates to the speed. So you have the speed in, and that helps you by transforming this time block to the angle domain. And then down here, you can select multiple bearings, general bearings, where you have one or two probes you select here. And the setup for those probes, you can define the angles they are mounted in compared to the keyphasor, and that is the basic setup for that. So let's do some illustrations of this display types. So I'll go to that file, display types here. Okay, so I'll just need to go and switch project back to something that is not outputting sound. Yeah, okay. The resolution in this room is a little smaller than I'm normally running with, but you can see here we have orbits that are measured from the X and Y probe. This is just a simulation you can also look at afterwards. So we have the X and Y probe here, and based on this waveform you see here, it goes up and down in speed. You will have a certain kind of movement of the shaft. And if we just extract the filter out, the first order, so this is order tracking. It will follow the speed up and down and always look at what is the vibration level that happens once per revolution. Then you can see that this is having an amplitude of this size, and the phase is starting at this position. The same goes for 2x, where it is two types, two vibration periods per rotation. That is called the second harmonic, or the 2x. And there you will also get an indication of the amplitude and the start of the phase. And together they create a signal like this. This is just a simulation, so if we imagine that you change the offset of the shaft, you can then follow the position of it together with the speed it was at. So this is what we call the shaft center plot, and you can also overlay that with the orbit plot. We have border plots and polar plots. On the polar plots you can follow what the phase is for the different probes and the different orders, and you can see that if it goes over resonance, for example, it will increase in amplitude and it will change phase. So this is actually pretty useful to follow, that you ramp up and suddenly this one becomes changing phase and changing amplitude. Then we have also waterfalls, so you can follow in time, both in the frequency domain and in the order domain, what happens across speed and across time. And these are all things that you would like to look at in order to make sure that your machine is running as optimal as it should be. I'll give a real-life example of that, where we replay a file of engine. So I'll go to this project here and open this data file. So it will start in a little while. Okay, so what we see here is that the machine is ramping up. This is the speed of the shaft. And we can see that in the start, the shaft was lying at the bottom, so it's a horizontal shaft. And when it begins to speed up, it begins to get closer and closer to the center of the bearing. And you can follow the shaft center position and the RPM it was at that point. This is the actual movement of the shaft center. And here we have the magnitude and phase of the first order in a border plot. So you can see that now the phase is changing and the amplitude is increasing. That is also illustrated here on the polar plot, where the phase is moving out and also the amplitude is moving out. So we are getting across a resonance frequency of the shaft. It might be the first bending mode of the shaft here we're looking at. So this could be a run-up case that would be interesting to see. You would like to know those resonance frequencies so you can avoid being in operation exactly at those frequencies. And also you might want to test what the maximum displacement can be if you're running in those critical positions. So, as I said before, the first order is one vibration period per rotation, and that is related directly to imbalance. So, similar to when you're at the mechanical and getting new tires on, they will not be balanced, and he has to put on some kind of metal parts, spin it around, and the machine is telling him what angle it should be put on and how much in order to balance this. Because if not, it will have some kind of mass that are not centered. The center of mass is not in the middle, and therefore it will give a first order vibration. Then we have also cases with misalignment, where you have connections between shafts, and if they are having an offset in either angle or radial displacement, it will also give a first order movement and also a second order movement. And the worse it is, the more harmonics will actually be excited like that. So in that way, individual orders can give some indications about what phenomena is happening on the machine. And that is also a little example of that with the first and second order simulation, where we can look at this one. So if we say that we have an imbalance, we can turn up the first order movement. And when doing that, we can see that we get a first order over time measurement in the waterfall plot. We will have a magnitude out here. And that is the size of that radius in that plot is equal to the amplitude of the first order. If we then also add a second order component to it, we can see that now we will also, on the filtered one, have the amplitude shown here, and the raw orbit containing everything will have a shape like this. And then we can also add a subsynchronous component to it, which is something that happens less than 1 time per revolution. Then it begins to have some movement in it in one revolution and some other movement in it in another revolution, and that's why it looks a little like this. When we want to take care of, for example, imbalance, we can use our rotor balancing application where we go in and mount an accelerometer or a prox probe, and we measure the speed. And based on that, it can tell us exactly where to mount mass in order to make the center of mass aligned, and the vibration level will become less and less the more you do this. So if you have any interest in rotor balancing to this, we can talk more about that. Just come to me. Also, if you want to compensate for some irregularities on the shaft, let's say that it's not totally round, and it's not really important for your analysis, so you want to compensate that away. You can, at a slow speed where you don't have any dynamic motion running, you can create a measurement of only the irregularities of the shaft, and then you can compensate that away. So next time you are doing the analysis, it will only tell you about dynamics that happens that are not related to such things. And the same thing goes for harmonic compensation. We can also handle that, and you can also do reference orbits where you capture data at a certain state of the shaft, let's say at one speed in one operation mode, and then you can capture different modes in different speeds, and then you can overlay those and have as references to your running mode to see if there is any important changes. It's always easier to do analysis if you have something to compare to. We also, as I said, do a subsynchronous orbit analysis in this application, where we are tracking the highest amplitude that are lying below the first order component. And that can happen in some cases, also multiple of them, but one case could be when the oil film inside the bearing will begin to behave a little different, and that can happen sometimes if you are getting across the first shaft resonance, where instead of the orders normally just follow the speed. But in some cases, this oil film here begins to actually stick to that first resonance frequency. So this is a little different. Here we have an order component that are actually not steady, but at some point it will begin to change with speed. And that's also why we treat that a little different. So you have outputted both the order and the amplitude of that component. Yeah, so I think this is more or less what I will be telling here about the basics of order tracking and orbit analysis. And then I'll give the word to Ozren.
Okay. Can you hear me? Okay. It's good or not so good, I don't know. So, my name is Ozren Husnjak. I work in VESKI. VESKI is a creation company which has recently, maybe year and a half, become a member of the Dewesoft. And some of you that might have been yesterday at the opening ceremony, maybe you heard the other Ozren from the company, so we are not the same Ozren. Ozren Orešković, our CEO, he was showing a small presentation about what we do, what we monitor. And one part of that was also the air gap monitoring, which I'll try to address a little bit about in this presentation. And then later Metod will help me because we are transferring our VESKI knowledge into the DewesoftX, so Metod will help me with a small demonstration. So what is an air gap? Where I guess you could joke about it and say that we try to make money out of thin air because we're trying to measure the distance of air. So for large hydro units, not necessarily hydro units, but electrical machines which are equipped with salient poles, which are equipped with these electromagnets that you see here. So here is a top view of a typical hydro unit. And here is, let's say, the difference of this, which is a rotating part, which is part of the rotors, and this part here at the top, which is part of the stator side. And the air gap is actually a very tiny, very small, getting smaller and smaller part through which the entire energy of the unit is coming out. So here as well the electrical mechanical conversion is occurring, and then of course the stator is connected to the transformers, etc., to the power lines and so on. That's how you basically and the problem which is becoming increasingly important is that in 30 years ago or something, for a unit which had 6 meters diameter and 100 megawatts, the air gap was about 30 millimeters, so pretty large, let's say. And the room for error was, the errors were allowed, not too much error, of course, but nowadays when you see a unit and it has 6 meters, it has 100 megawatts, but the air gap is reduced. And the more error you input, and of course with operation there'll become additional problems, the more error you introduce during usually the manufacturing or assembly stage of the unit, the more problems you might have. Just to illustrate, and this is as good as the mathematics I can get, so for a unit of 10 meters diameters with the air gap of 20 millimeters, and with typical numbers of how much you would tolerate the stator tolerance and the rotor stress, which is about 5%, you get about 10% tolerance, which is 2 millimeters. So for the air gap as a size of the bore, as a function of the size of the bore radius, it's only 2 parts in 1,000. And when you consider these tolerances for the air gap, you come to 2 parts in 10,000, which is kind of better than a Swiss watch when you think about it. So it's quite extremely precisely built, and it would be good enough if it was just standing, but then it runs, and then you experience a lot of if it was just standing, it would be enough. So this is another picture, maybe just to illustrate for those of you who didn't have a chance to see a hydro unit alive. So it basically consists of something called the rotor spider, which is shown here. Then you have something called the rotor rim, which is basically a set of laminations which are interleaved. It's a steel plates about this thick. And then on these laminations here, which you can also see here, you put the rotor poles. And as we said, these are big electromagnets through which the current is flowing. and which helps in transferring the energy to the stator side. So this is an example of the rotor pole. They're actually not screwed or fastened with some bolts or similar to the rotor rim, but they're actually keyed to it. Otherwise, the forces, the centrifugal forces, would be too large, and the thing would probably crack and fall apart. There is a reason why they are keyed to the rotor rim. Now, of course, if you have a rotor out of round, which means it's not perfectly circular, of course, this can cause effects on the stator. The stator might be, not necessarily, but if there are tall machines with a large stator core, then it might be flexing at 2 times turning speed frequency, which is something we see not very often, but we see it in some machines. But and this can, of course, affect the core clamping, etc. So it can give you a lot of issues with the stator. But probably the more common issue you see when you have a unit which is running in mechanical rotation, and Søren kind of mentioned the balancing to be a thing to go with if you have a first harmonic. But sometimes when you turn on the excitation, which actually means you are putting current through the rotor poles, you might see a totally different situation. So for one vector which you're trying to balance, which is mechanical, you might have totally opposite when the unit is exciting. And it's sometimes hard to balance that. If the vectors are small, then you can do it, but sometimes you might need to do additional stuff. So basically, these rotor balancing issues might be a problem. For stator out of round, what you see, so you have 2 circles, stator and rotor. If one is off center, this will be, when you turn on the excitation, it will be pulled to this side. Of course, the bearings would not allow it to go all the way, but then the bearings are suffering, and they might be overheating, and so on. And also the rim, because when you think about it, it's a large structure, 2 RP in length, and it's pretty flexible. Shouldn't be, but it is. And so it can kind of flex on the spider, and this can cause fretting and all kind of additional issues. We've seen cases where the keys holding the poles to the rim or rim to the spider were falling out, etc. So you can expect problems. And what do we use to measure the air gap width? Well, if you want to see it in live and if you want to feel the sensors, we have at the booth just 5 meters from here. So you can go check VESKI booth, but basically what we use is the capacitive gap probe. Different sizes for different air gaps. The bigger the air gap, the bigger the sensor. But they are basically measuring distance. So this is they work on capacitive principle. They must be immune to electromagnetic fields, etc., to dust, and so on. Depending on the size of the unit, you're gonna want to use 1, 2, 4, 8, or plus sensors, which you basically glue to the stator core. You see the black dot. I'm not that tall, but you can see the black dot there. That is the air gap sensor. So in this configuration is for 4 probes. And this is kind of a rule of the thumb, how many you want to use depending on the stator diameter. So here, in this case, you have 8 probes. Sometimes if the stator is tall, you might want to use it in 2 planes to see how it's expanding with thermal heating. Once the unit is heating up, once it's on load, so you're going to be able to see how the top portion is expanding relative to the bottom portion. So you can introduce problems, of course, in all stages of the unit manufacturing, even in the design phase, but probably mostly in the construction phase. You might make the rotor out of round, or you might make stator out of round. You might put the rotor somehow offset to the stator, so it's eccentric to the stator, etc. But more importantly also that during the operation, there's going to be additional problems like the rev movement. The entire rev might be loosening up. You will see a small example of that in the next couple of slides. You might have loose poles. So the poles are, as I said, keyed to the rim. They might be loose. It's not very common, but it happens. Of course, you might have shorter turns. Sometimes that's why sometimes we combine the air gap measurement with magnetic flux measurement and so on. And if you have more than one sensor, you can see the rough shape of the stator, which is what we also do. And of course, here's just a list of different problems that you might capture using the air gap technology. More sensors means more data. Sometimes for a smaller unit, one sensor might be enough. If you're worried that you have problems with the rotor, it might be enough. So here's a kind of a table what you can extract using 1, 2, or 4 and plus sensors. So of course you can see the minimum air gap when each pole is passing. You can see at which pole it's occurring. And I must say you must also use the trigger sensor, or you probably heard of keyphasor or diagnostic trigger. So that sensor which is giving once per revolution, so that you'll be able to number the poles correctly. So it's air gap is rarely used without the diagnostic trigger or the keyphasor. So, and of course you get the rotor pole profiles because you see all the poles, etc. If you use 2, you can kind of imagine that, and Søren did mention that you use 2 proximity probes when you measure the orbits between the bearing. Kind of a similar thing you do, but only for the air gap. So that you can extract the orbits, the rotor statical center, the rotor dynamical center, so current axis of rotation, etc. With 4 and plus sensors, you can say also some things about the stator, and one of the most important is this red. So you can kind of compare the real rotor, which is moving within the air gap, and it's also orbiting within the air gap. So it's not just a shape turning around the one axis, but similar to the shaft in the bearing, it's also orbiting. Comparing this to the interpolated stator shape, you can get kind of the idea of where that air gap minimum is. And I will show you on the next slide the most important picture that we get, and which we are now transferring to DewesoftX, which will be soon, we hope, because we are working on it to put it a part of the DewesoftX air gap model. So this is kind of the thing that you want to extract. This is the rotor shape. This is the interpolated stator shape. It's orbiting. It's not just moving around this statical center. It's orbiting. Here is an enlarged orbit of that. And you kind of push the button, and it tries to figure out where this air gap is and for which pole. And that is the main result that you get from these models, along with rotor circularity, concentricity, and stator circularity and concentricity. So, yeah. Okay, just to mention a couple of more things that we extract from the data. Once you have your raw waveforms, you calculate by pole number. So this is a American unit, 72 poles. You can see on the x-axis is the pole number, and we extract the average value of all poles, maximum value of at any particular pole, minimum value, and we extract something similar to the first and second harmonics that Søren mentioned, but we do it for the air gap. And the mathematics is a bit different, but the results is the same. And then we can compare, of course, how much because you have 2 sensors on opposite sides, you can see where the rotor is positioned, how much eccentrical it is, etc. So here is some tables. There are still no standards, but recommendations of the numbers that could be okay up to critical. Yeah, but not everything is written in stone. So sometimes we see units with bad circularity behave better than the ones that have good. So yeah. Anyway, let me give you an example, and then I'll hand to Metod. This is just a small illustration for one unit, and it's US unit also, which strangely looked kind of, you see the shape of the rotor, and rotor circularity is about 9%, and it's at 30 RPM. So it kind of looked uglier when it was stopped. There is a reason for that, for those of you into electrical machines, because it is something called a shrink fit rim. They put the rim, they hit the rim, they put it on spider, they wait for it to cool down, and it's pushing inside when it's stopped. That's why the unit is uglier, the rotor is uglier looking for a small RPM than when it runs up. You see the speed is running up, it becomes better. So it's still unexcited, still there is no current flowing through the rotor poles. At the next step, the unit is excited, so there is some change in the shape also, as you can see. But then at some point, the unit goes on load, and what happens is at some instance, the load is rejecting, something happens, lightning strikes the electrical lines, the unit will then, of course, the energy has to go somewhere, it cannot disappear, and then it goes into, the unit increases its speed. So you will see now what happens when the unit increases speed. At 110 RPM, still okay, reasonably looking shape. You see also as as it comes to 139 and then later at 160, the orbit within the air gap is increasing. And so we get all that from those first harmonics in the air gap, and we can say how close to actually hitting the stator it is. So yeah, I think we should switch to the demo. Thank you. Metod, can you?
Okay, I'll take a seat as I click around. So I hope that by now Ozren has convinced you that there's quite some domain knowledge behind their solution and their analysis software. And since VESKI became Dewesoft, a member of Dewesoft family, we are on a trajectory to move this domain knowledge onto our platforms. VESKI has done some great work moving onto our hardware, but we want to do the same with the software as well. So what I'm going to show you here right now is something we're working on. So it's a kind of work in progress kind of demo or a sneak peek, if you will. But we want to implement analysis, air gap analysis inside Dewesoft. So also the software and the analysis will become, first-class citizen of Dewesoft ecosystem. And for that purpose, we have developed a new air gap analysis math module, which kind of it fits in with other maths very nicely. I have a little bit issues with resolution here, but we'll manage. So here we have a scenario when we have 72 poles, and we can set various stuff about how our machine operates, like whether the poles are ascending with respect to rotation direction, what's the rotation direction, and so forth. We have input, so we can capture the angle and the speed of rotation. And you can choose from a variety of different sources that you are, I believe, familiar with and are available in other math modules inside Dewesoft. And then, you can have a number of outputs, and most importantly, at the low, in this lower part of the UI, which is a little bit squeezed right now, but nevertheless, you can configure a number of sensors, and for each one, you can specify what is the first pole after the tacho, so you know how to align the signal with the sensor, and also you can assign the physical position and also the type. So we support the gap sensor and magnetic flux. We combine both in this solution. Now, if we move to live view, you'll see that these signals are resemble a little bit the signals you saw in Ozren slides. So these are the signals from 4 different sensors, and this typically is how they look like. So they have this kind of inverted spike or a dip when the pole passes the sensor and the gap is minimal. So that is this point here at the bottom, for instance, denotes a point where a particular pole is closest to the sender, and the gap is minimal. And one of the first steps in the analysis is to extract the pole profiles. This is the gap as a function of pole number. This is the same kind of graph Ozren showed earlier, right? And because we are measuring the same rotor, they kind of all exhibit the same shape. And we use the information about the first pole after the keyphasor to align those poles. So you get basically a very similar response from all the sensors. Now, based on these pole profiles, we do some kind of statistics. So for each pole, we determine the minimal gap, the maximum gap, the average gap, and so forth. And then one of the first steps you want to do when you measure machine is measure machine at low speed, or where it's not, when it doesn't undergo magnetic stress and thermal stress and so forth, and that is to measure it. And we have implemented this reference measurement, which you do in this calibration menu, which you may know from other methods. So we can perform it live right now as the measurement runs, or you can do it in post-analysis on any part of the data file you choose to. So if you have a long recording, you can just focus on a particular interval and average over that. So I can just simply select it and do the calibration, and now it's registered. So if I move back here, so we have this average gap, reference gap calculated for each of the sensors. Okay, then we have also improved our orbit. We have also improved our orbit graph, which is used in orbit analysis to accommodate or to show this data that is outputted by our air gap analysis software. So let me maybe increase line thickness a little bit. So this dashed line show the ideal stator shape, and then we have this deformed stator and the rotor shape. We can highlight the current pole, so I can change it to something else, and I'll have it shown somewhere else. We can also have the zoomed out, zoomed in region of this orbit. And of course, you can choose to show the minimal gap, and it will show at which angle the minimum gap occurs, and also for each pole. Yeah, so that would be a short demo of something we are working on. So we are on a trajectory to move all the wealth of domain knowledge onto our platform. So thank you.